So in this question, we can see there is an unstretched spring that is at equilibrium, but then a mass is put on it, and it's slowly lowered until it reaches equilibrium. So this is the equilibrium unloaded, this is the equilibrium loaded. So we get to this new length, LEQ. The block is then pushed down. Someone's hand comes in here and pushes down on this thing, and it gets pulled down to L compressed. And then it's released. After the release, at what height will the kinetic energy of the block be a maximum? At what height would it be a maximum? So, if we compare this setup to a horizontal spring, we have a spring attached to a wall, and there is a block. And this is the equilibrium position, and that's like this one below it. What we do then is we stretch it to here, or we compress it to here, which is the case here. We have compression. We compress it to here. And when we release that spring, that potential energy is going to be converted into kinetic energy, and it will reach a maximum when it gets to this equilibrium point. Well, this is the equilibrium case, and this is being disturbed from equilibrium. So this is the minus XO, if you will, the maximum amplitude that we get, the maximum displacement. So we would expect the maximum kinetic energy to be when the block is going through this equilibrium part. After it goes past this distance, it's now stretching the spring, and the kinetic energy is doing work on the spring as well as gravitational potential energy, but it's stretching the spring. So it's going to be a maximum velocity at L equals EQ. Now, the challenge in this question is really visualizing what's going on here. And that's why it's important for us to have a standard example to which we can compare all novel new situations. And that's 18.